And now it's action time! Let's implement a 4-bit Gray encoder, a 4-bit Gray decoder, and a test bench for them. For this project you are going to need the following Verilog files: Gray encoder 4bit.v, Gray decoder 4bit.v, and testbench Gray 4bit.v. Please use the same project structure as we used during the video Hello World using Verilog and Modelsim Student Edition. If needed, you can find a link to the video in the description. Encoder implementation. Let's analyze now the block schematic for the 4-bit Gray encoder. The circuit is extremely simple and it contains only 3 XOR gates to interconnect the binary inputs values. The Verilog code for this combinational circuit is extremely easy to implement. At lines 5 and 6 we declare the 4-bit I/O ports. The input contains the binary value while the output has the gray value. At lines 9 to 12 I implement this circuit using the Verilog dataflow style that has continuous assignments. Take your time and analyze how each gray bit is constructed from the binary inputs and the correspondence between the code and the circuit schematic. The dataflow style is a popular solution when you need to implement a simple combinational circuit. In the top right side we have the synthesis results for this Verilog code for an Intel Cyclone 5 FPGA. As expected, the circuit looks exactly the same as our block diagram from the left. Decoder implementation. Please make a new file called Gray Decoder 4bit.v with the following content. As you can see, the block diagram of the decoder is extremely simple and is also built from 3 XOR gates that have the gray bits as inputs and the binary value as outputs. The gates are arranged in a different way than in the encoder, being put in a cascade formation. The Verilog code for this circuit is also very easy. At lines 3 and 4 we declare the I/O ports, which are the gray input and the binary output. At lines 7 to 10 we implement the circuit using the dataflow style. Take your time and analyze the correspondence between the circuit schematic and the Verilog code. Let's analyze the test bench. Please make a new file called testbench Gray 4bit.v with the following content. The testbench architecture is very simple and it instantiates the encoder, the decoder, and connects them together. If the encoder and decoder work correctly, then bin out value should be the same as the bin in value. We will inspect the gray code bus visually and correlate them with the table of 4-bit gray code values. Here is what the Verilog testbench does. At lines 5 to 7, we declare the testbench variables used to connect with the DUT. We use the reg type for the inputs and the wire type for the module outputs. The 4-bit gray code wire is used to connect the output of the gray encoder with the input of the gray decoder. Remember to always use the wire type to interconnect Verilog modules. At line 12 we instantiate the encoder, then the decoder, and connect their ports with the testbench variables. The initial procedure from line 23 is used to display any change of the bin in, gray code, and bin out variables. The procedure from line 28 is used to change the bin in value between 0 and 15. After you simulate the test bench, you should see the following values printed in the console. You can easily see that the gray value codes are the same as the ones from the table and how they are reflected over the red dotted line. The sole difference between the reflected values and the initial values is the value of the most significant bit. Another thing that we observe here is that bin in and bin out values are equal, so our encoder and decoder work great together. What do you think about this easy example? How do you like modeling combinational circuits in Verilog?